Okay, well, welcome everybody. Hi, good afternoon, good evening. Um, we are profusely apologetic for the technical difficulties. There's some ultimate irony here that we are congratulating Reinhard Genzel for winning the Nobel Prize for observations of the center of the galaxy while we are unable to get a Zoom system to work. So we are sharing Reinhard with you via, I think it's like a three-way. There's a Zoom and then a FaceTime, and then I'm not even sure what else. So at any rate, Carol, who is you're going to hear from directly in a moment, referred to the black hole at the middle of the Berkeley Zoom system. So at any rate, Reinhard, welcome. We are so grateful that you stayed with us through all these technical difficulties. Good afternoon, good evening. I'm Frances Hellman. I'm Dean of the Division of Mathematical and Physical Sciences. I am so delighted to see you all here to celebrate this just remarkable occasion. Reinhard, congratulations on your Nobel Prize. Congratulations on a lifetime of discovery. Thank you for taking time out of what has been, without question, a crazy day to share some of the joy with your friends, your colleagues, and this many students here at Berkeley. We are so excited to have you on the phone and so proud of your accomplishments and just want to say thank you. So here's what's going to happen today. There are a few key people who want to congratulate you and thank you for starters, including Chancellor Christ and our Provost Paul Alvarez, the Astronomy and Physics chairs Joshua Bloom and James Analytis, and then Saul Perlmutter, with whom we celebrated the Nobel Prize just 9 years ago in 2011, is going to moderate a conversation about your discovery. So I will now hand things over to Chancellor Carol Christ.
Thank you, Frances. I'm delighted to join this gathering today and to welcome a new Nobel Prize laureate to Berkeley. What a great day for Berkeley and for the University of California. As you all know, astronomy and physics professor Reinhard Genzel was awarded the 2020 Nobel Prize, together with UCLA astronomy professor Andrea Ghez, for the discovery of a supermassive compact object at the center of our galaxy. This seminal work has brought us further and further into observations of the center of the Milky Way and into our understanding of supermassive black holes. Reinhard, your perseverance in this study has been remarkable. Folks may not know that some of your initial observing in this area was done as a postdoc here at Berkeley. You worked with our late, great Charlie Townes, also a Nobel laureate. I can't imagine a more profound academic lineage than that, and I thank you for passing along your knowledge to generations of students and collaborators here at Berkeley. I wish we were all together to celebrate. Reinhard, it's at this point in the ceremony that I would present you to the most prized of Berkeley perks, a Nobel laureate parking spot. I hope that when things are back to normal, you'll visit and you'll park your car. Seriously, thank you for providing this wonderful news and for showing the world that Berkeley is one of the best places to study in the universe. And now I'm going to hand over the podium, the virtual podium, to Paul Alvarez, the Provost.
Thank you, Carol. Reinhard, warmest congratulations. It is such wonderful news. I think every scholar wants to be able to peer into the center of things, but you really did it. And we're just so delighted with your perseverance and your discovery. And I just wanted to add that we are all here in some ways trying to serve the public by discovering new knowledge, by finding out things that people didn't know before. And there is a beauty to that. And so you have truly honored Berkeley by finding something that people did not know in the most fundamental way possible. And for that, you have served the public of California and the university in such a wonderful way. So we are so grateful to you. And of course, we're looking forward to hearing from you some of the stories of your discovery. I'm going to hand it over now to Josh Bloom.
Reinhard, on behalf of the entire astronomy department, congratulations. We're so proud of you as your colleague, as your friend, as fellow scientists, and as members of the greatest public university in the world, the University of California. Your work and that of Professor Gez's reminds us all of the seminal importance of astronomy in the study of fundamental physics. It continues the long line of remarkable insights from the heavens, from Ole Romer's determination of the finite speed of light in 1676, Jensen's discovery of helium in the sun, the first confirmation of general relativity in 1919 by Sir Arthur Eddington, Vera Rubin's discovery of dark matter, the existence of gravitational waves, indirect and then directly from the dance of neutron stars and black holes, and yes, the accelerating expansion of the universe. Your remarkable discovery about the existence and the nature of the black hole in the center of our galaxy proves just what a remarkable laboratory the universe is. In your work, we are also reminded of the importance of the versatility, persistence, and the leaps of faith that we need in building new facilities and instruments to study the heavens. The science drivers behind the Keck telescopes didn't contemplate extrasolar planets, dark energy, or measuring the orbits of stars dancing around an unseen monster mass in the galactic center. While we build to solve the questions we know about now, we often find the most important questions of our future are the ones that we haven't even learned to ask yet. Here's to you, Reinhard. Congratulations. Now let me turn it over to the chair of the physics department, James Annelius.
Well, what an extraordinary day. I can't tell you how pleased I am personally, but also on behalf of my colleagues in the department to receive today's announcement that Reinhard, you have received the 2020 Nobel Prize. And so congratulations to you. I feel so privileged to count you as a colleague. And of course, the Nobel Prize recognizes your seminal work in the understanding of black holes, in particular, your pioneering observations in the motion of celestial bodies around the galactic center, but also they led to the understanding of the supermassive black holes and at the center of the Milky Way. And of course, and Reinhardt's recognition and his achievement follows a long tradition of Berkeley physics pushing the frontiers of our understanding of the universe. Of course, following George Smoot's Nobel Prize in 2006 and then Saul Perlmutter's Nobel Prize in 2011. This is an achievement that is so few others, and you have served our community in a way so few others can. Because of your achievements, we are going to continue to be able to keep Berkeley physics at the forefront, attracting the best scientists, students, and physicists from around the world to continue in this tradition. So thank you, Reinhard, and congratulations again.
So I was going to pick up and offer my congratulations, Reinhard. It's wonderful news, and of course I was asked to get a chance to chat with you a little bit and moderate. And this is an amazing picture. I'm getting to see you through 3 layers of modern technology. I think it's emblematic of our amazing ingenuity that we can actually still see you amidst all this. And it's amazing, and I can even hear you. So I will do the ridiculous thing of having an interview with you while you talk to us through 2 layers of cell phone, and let's see if it works. But I imagine that this is only one of a myriad number of surprises of your day today, and so I should just begin by asking you. So how was your day? I was going to say I wish that you had been here in Berkeley for this day for obvious reasons. Among them is the fact that you would have gotten woken up at 3 in the morning and you could have shared that that bizarre aspect of the early wake up. But it's even better you get to actually be alert as you get the phone call. So tell us a little bit about your day. What's it been like?
Hello?
Ah, I think we have you. Can you hear me?
Yes.
Excellent. Much clearer. And can everybody hear me everybody hear all of us on the Zoom?
Okay, well, we can't see each other, but it doesn't matter, I think. It's all right.
That's me, yes. And we have and I have you by the Zoom, so I think everybody can hear you. So
Okay, so I'm very sorry for this. As I said, all of us are world-class professional Zoomers. That's what we do all day long.
Exactly.
And it's working. It's been working all day long and all month long. And here we have this little thing between Berkeley and Munich, which doesn't work. I'm very sorry.
No, and Reinhard, I think it just is demonstrating one of the questions I was about to ask you, which was when we were trying to do these kinds of projects, something is always going wrong, and that most of what we do is just try to figure out how to make it work better the next time. So I was actually going to ask you if you could give any feel for, this was many years of work, and I'm wondering, were there moments where it felt like it wasn't going to work, and then were there big great moments where suddenly you felt, now we've got the next stage?
Oh yes, of course. I mean, you must have had that. You had that. I guess for us, the biggest thing in the last years was to get the interferometry going. If you may recall, Charlie Towns' dream was to do this experiment we have done already in the 1970s. And he in fact did this fantastic pioneering experiment doing basically, downscaling or bringing the infrared waves down into the radio through heterodyne techniques. But that was very, very, very low sensitivity because of quantum noise. And so the result was, and if you want to read about this, you read it in the annual reviews. He gives his biography in one of his volumes, that he knew he would never get to the galactic center, which was a real disappointment to him. And to give you a feeling, what we had to overcome to do what we're doing now, we had to do better than Charlie by a factor of 100,000.
Wow.
And so really that was the breakthrough, that we were able to do this. I talked to Towns, the gravity development took 10 years and more, and so Towns was alive during quite a bit of that, and he was very interested in it. But there was one thing he didn't like about it. It was too big. There was always one condition with Charlie, which I don't agree with, and Saul, you should comment on this, which was above a certain scale of experiment, he felt that was not right for the university. You should always have students work on it, and so then, if it was getting too complicated, you had to have many engineers involved, and you shouldn't be doing things, not at Berkeley. It was always his conviction. There, I disagree with him. I think, certain scales require that you have to have more sophistication.
No, in fact, it's one of the ways to teach the students, that they get to learn how to do these kinds of sophisticated experiments. And what was your experience actually with students and postdocs, on this project?
Oh, very good experience. I mean, in fact, we had initially student, later on postdoc, who was one of the leaders of the experiment next to our genius leader, Frank Eisenhower. But I mean, not many, but some students clearly who had the burn, who had the interest, who had the wish to do this, of course can do this. I mean, there's no limit to this, but you have to apply yourself. That's very clear. And Towns, of course, Towns knew, but he was not willing to go beyond the scale of, as you said, what the graduate student could do. That I don't agree with. And I mean, what you've done at up on the hill, of course, shows that is definitely true also for the dark energy project.
I think it's also saying that you were working in sort of one of those roles where you're in both physics and in astronomy. And I think the traditions of physics were obviously in the particle physics world. It made people much more comfortable with these very large engineering elements of a physics project. And so I think I might have given a little bit more room for maneuver.
Yeah, but you see, you understand. I mean, for those of you who know what Charlie Towns means, at least in terms of the concept, Charlie's success on the maser and the laser was driven by students.
Right.
It was not doing it big. And in fact, if you all recall, he didn't do the first big ruby laser because he knew that industry was about to get onto it, and so that's where he stopped the laser. And he went elsewhere. He went into nonlinear optics at that time because you can't have a graduate student do a major part of a project in a career of 5 years or 6 years or something like this. You shouldn't be starting it. And so that was always his philosophy. As I say, I don't quite agree. And that's actually, if I may say, if I make a comparison between European astro research and the American astro research, this is where the American universities are beginning to fall behind because naturally they cannot always concentrate on the research. You have to do teaching, and so this is a difficulty for Berkeley actually.
And I'm curious, in practice, what was it that made it possible to make that? I'm just getting back to the science for a second. What was it that was possible to make that 100 and 1,000-fold improvement? What were the steps? Was it? I assume it was little bit by little bit, not in one big fell swoop.
No, it was one big step, but very well thought through in three major categories. The first step was you've got to work on phase referencing. You cannot hope in the coherence time in the infrared, which is a millisecond, to reach sensitivity levels which are good enough that you can track on the fringes on a star in the galactic center, in the inner galactic center. So you have to first do the adaptive optics, which means you have to separate, you have to flatten the wavefronts on the big telescopes with adaptive optics. So that's known how to do. The next thing you have to basically align the piston phases of the different telescopes through using a bright object in the field of view. In the galactic center, fortunately, there are such bright stars in the infrared. And then the third step is you have to have the capability to pick up the fringes on a second object, which is your science object, once you're already on the brighter star, have stopped the fringes. And so that made a jump right there of a factor of 1,000 in sensitivity to stop the fringes with a brighter star, and then you can integrate 10 magnitudes down. The second thing, of course, is even better. Charlie knew that. Even better laser tomography through the whole system, so that you would have, that you knew the phase everywhere. And the last one was detectors. We were able to develop a detector which, in the near infrared, had no read noise at 10 kilohertz read noise, at 10 kilohertz readout. So that was very, very important. But then there were also, as you say, these moments when it just didn't work. What in our case didn't work, we would go into a door in order to have a very compact system in the quiescent and cryogenic environment. And therefore we did all the beam reflections and so forth in single mode fibers. Unfortunately, when you then want to do the metrology with lasers, you send lasers, typically 100 microwatts, back out the telescope to the telescope through the fibers. The fibers, have a little bit of Earth's impurities in them, and they make Raman scattering back to the detector. And when we switched on the first time our system, we had 1 million times more photons than we expected to have, and that was a big fight to get those photons out of the system. But other than that, we had some really genius types on the experiment, both in France and in Germany. And then the beam combination in basically commercial beam combination technology, like in radio telescopes, you make the beam combination in waveguides.
And I'm curious, what was the trick that made it possible to suppress the sexual Raman scattering from the impurities?
Well, we changed the laser around, and then we did the trick that from the detector itself through the fibers, which were the differential delay line, which is a 20-meter hoop of fibers which made the scattering. We started off with 100 nanowatts, and then after you threw the fibers on the outside of the instrument, we heterodyned up the power by a factor of 1,000. So we basically didn't have as much power in the single mode fibers.
And so then you didn't have to worry about as much scattering from that source.
Yeah, well, we still do have to worry about it. We are now so sensitive that we have a new detector. Yeah, we're actually in the process right now of pumping up the sensitivity of gravity by another factor of 100. Makes it extremely powerful machine for resolving broadline regions around quasars and also do exoplanet spectroscopy. Oh. The best current exoplanet spectroscopy comes from gravity.
Ah. That's great. So it's you're going to do even much more science with these same techniques. Getting back to the discovery moments, for which the Nobel Prize was awarded. Were there any particular runs that you were doing where you felt that those were the moments where you would say you were actually able to say a much more definitive statement about the black hole than previously? Was it?
Yeah, well, of course, that was not our doing or Andrea's doing. It was nature. They gave us a star, which was on an orbital time scale of 16 years. That was not supposed to be there. It had to, one has to ask Andrea how she sees it, but certainly the fact that we all of a sudden, when we went on from just measuring proper motions in the 90s to actual orbits, the orbital timescales of most of these stars are hundreds and thousands of years.
Right.
So that's even longer than a long-lived Berkeley professor. So clearly, we were lucky. And Andrea actually recognized that there was one star of the ones which we had tracked, which were close to the black hole, which might have an orbital timescale where you would hope to see it again. And then so once we knew that star, which we saw Perry in 2002, would be back in 2018, that's when we started on gravity, because we knew next time when that thing comes back, we want to be able to do GR tests.
Right. No, in fact, what's I remember actually I was doing a Keck run on one of the same nights that on the other Keck when Andrea was starting this back around that time. So I guess I must have seen one of the very first timelines before it started pulling together. So when did you?
The next thing, let me say something about the next step. Of course, I've been asked many times today by the reporters about the relationship between Andrea and me, and let me for everyone in Berkeley comment on this. I very much appreciated the competition initially, I would say at least, because it was like we were both sort of artists on a big scene, and the audience, the scientific audience, was in a perfect position to see us perform the same exercise and then judge whether the outcome was the same. It's just perfect scientific principle.
Yes.
So when the two teams would agree, the audience immediately would believe what we have, because come on, Europe would certainly not agree with California and vice versa if it wasn't right. So that wasn't initially very much of an advantage. I would say the last years, I at least knew that the interferometry was a unique thing of the VLT, because we had 4 8-meter telescopes, the infrastructure was already there, et cetera, et cetera. And I tried to convince Andrea that we should basically go from a competitive stance, which we have done successfully, et cetera, to a collaborative stance, and I still will do that. And in fact, we exchanged wonderful email today. We will have a COVID distance champagne event together.
Excellent.
In the next few days.
Excellent.
I hope. And pardon?
No, I just said excellent. That's exactly right. Go ahead.
And that they come back together, because you see, the interferometry is extremely expensive in terms of telescope time. And so if we could combine the strength of the kick on the spectroscopy, and then basically take more of the time on the interferometry with the VLT, everyone would win.
Yes, yes. No, I know the advantages of these of having a great competitor from personal experience. So that's a great story. Actually, I was going to ask if Jessica Liu is on here, because I know that she has been involved with and collaborating as well with Andrea. Jessica, are you there?
I am.
Oh, just
yeah, congratulations. Yeah.
Maybe,
I just want to say my congratulations to Reinhard too. It's such a pleasure to see astrophysics and black holes and the Galactic Center in particular be awarded such accolades, and well-deserved. Congrats.
And I was just going to ask from your view, Jessica, what were you seeing in the stages that you were working on?
So I joined the Galactic Center group at UCLA and using Keck at University of California back in 2003. And at that time, the suspicion that there was a supermassive black hole was very strong, and there was some tentative evidence. And really, it was the speculators who were saying, well, maybe it's not a black hole, maybe it's a swarm of dark stars or quark stars or something else exotic. And so we really were in the grungy fight of proving every alternative scenario wrong, and that it had to be a supermassive black hole with stars orbiting the dark beast at the Galactic Center. But as a junior astronomer, I was a graduate student of Andrea's. It was just very amazing to go to the telescope and see stars move in real time, while you come back the next night or the next month or so later, and they've moved, and a year later you can see them moving by eye. And yet to imagine those stars being, tens of thousands of light years away, and the speeds that they're moving, fractions of the speed of light, significant fractions of the speed of light, approaching within solar system scales of this beast of a black hole. It's a pretty amazing experience as a junior astronomer, and to have a role model like Andrea to pave the way, and a friendly competitor like Reinhard to really inspire us to have great conversations and great ideas and innovations around the technology and the methods and the science itself. It's a real pleasure, and I've learned a tremendous amount and continue to work on the Galactic Center. There's no getting away from it. It's an amazing place to study.
So the center holds in this case. So do you were there meetings? Was this a small enough field that people all were coming to the same meetings together and comparing notes every 6 months, a year?
Yeah, every year or two. I fondly remember numerous conferences in Germany. One in particular, when I was a very young graduate student, I presented something controversial, and Reinhard stood up from the back of the audience and asked very pointed questions and made us defend our results. And that spirit of competition really led us all to be better. I don't know if you remember that, Reinhard.
I do. Yeah, no, I think it was quite a road. It was quite a trip, a long one, but a good one. And I think we're not done yet. I mean, Saul, you understand, we are not done yet. I mean, we have to understand that both the gravitational wave experiment, LIGO stuff, as on the stellar black holes, as well as the Galactic Center, as well as the Event Horizon Telescope, neither have demonstrated to a high degree of certainty that the Kerr metric is right.
Oh, so
if we want a no-hair theorem test, which is incontrovertible, we need to do more work. So to map out what we need to do is, I think the Event Horizon Telescope is first. They need to get a shadow. Let's hope that what they see in that is indeed a photon ring. Or at least if they observe a number of times, they can extract the photon ring. Once we have the photon ring and we have the mass now from the kick and our measurements to sub% accuracy, you have a sub% zero test of basically the mass of the black hole in two different ways. So that's pretty good. Then the next thing is the spin. For that, you need to have either a faint star inside of the S2 orbit, which you're looking for. We have found faint stars now. And or the Event Horizon Telescope has to be so good in terms of the shadow that they can actually extract the spin. That sounds quite tricky. The third would be that we can extract the spin on stars in the spectroscopic domain. That would require the TMT and or the ELT value. But Jessica can perhaps comment on that. And then, of course, eventually, I would say it's going to be LISA, because LISA seeing an extreme mass ratio in spiral, that would nail the problem completely. But please let people not say that we're done. In terms of testing and falsifying or verifying the current metric, we are not done yet. We have ever stronger constraints, but we're not done yet. That's exciting, but it unfortunately it probably goes beyond my lifetime. Jessica, you're strong. You will do that, I hope.
Or our students after us.
I think that probably the best part of all these kinds of discoveries is the fact that it kind of opens up all these opportunities to ask questions. If you've never seen a black hole, then all you want to know is, do they exist? Once you've seen that black hole, then you actually want to start knowing, okay, what's really going on, right? And so that now you're actually getting to play. So now, in some sense, the fun begins, especially as these technologies have made so amazing advances, right? And I think the technologies that you guys have developed, and then coupled with the technologies from the gravitational wave work, it just opens up something that we've never, it's hard to imagine that you should be able to do these things that we're going to do. So I'm feeling a little bit bad, I guess, first of all, keeping you awake, but I just want to see, were there any questions from our community here? Because I know that we have many people online. By now, I'm sure they've all just been shell-shocked by the amazing technology that we're using to communicate with each other. But if not, I thought they might have some questions for you about the prize today and about the results. And I was just going to see if there were any before we conclude.
Hi, Saul.
Yes.
This is George.
Okay. So I
wanted to say, as the older guy here, I wanted to say congratulations to Reinhard, and hopefully soon he'll get to go home and rest, because I know how hard it is for the first few weeks. You should tell people it's not exactly trivial what you end up going through. So relax some, Reinhard. It's a long way to go, and congratulations again.
Thank you.
So that was my next question. Whether your adrenaline is keeping you running. It sounded like you were up at the office at 6 o'clock in the morning today, and in your time, and which means that presumably this is certainly beyond bedtime. But hopefully you're still enjoying that thrill of hearing all this and getting to. And I think one of the best parts is just hearing from all your friends all around the world. So I don't know whether you've yet had a chance to even look at the pile of email.
Yeah, well, okay. Let's forget about the emails. You know about this. This is going to be a busy job to answer, which I want to do, actually. But I'm really enjoying to talk to you people. And I have to say, I feel very bad. If we would not be in the times we are in, I would definitely fly out to Berkeley next week just to see you all and reminisce of all the earlier times. I was very pleased, I should say, that I got mails today from all the 4 towns' daughters, because that is very important to me, because they appreciate, of course, in that sense, where this all comes from in in the first stage, and so Berkeley has played a big role in this.
No, I think that we will definitely look forward to having you come back, and we will definitely do something celebratory all together. As soon as you're back in town, and of course, wait until it's safe. So I do think that this heritage that you have now of having followed from one Nobel laureate to another at Berkeley is a great story. So just because now I'm feeling like we should give you a chance to go to sleep. I was going to ask if we can set up. Can we have the Zoom show everybody all at the same time, so everybody can give you a final wave and an applause. I think it would just be good for the whole group. Is there any way to set that up so everybody can see each other?
No, I tried it again. I just cannot penetrate into your the second wall you have. I don't know why that is.
Well,
never experienced this on another Zoom. What we could do perhaps is in the next 1 or 2 weeks set up a common seminar or something like this, where we go with a professional setup Zoom so that we can all see each other and then have a little discussion.
No, I think it's a good idea. I think we should definitely plan for a seminar with everybody here. And what we'll do right now is since we have a recording going of this Zoom, we will just ask everybody to turn their cameras on for a moment and send you a celebratory wave, and then we'll just email you the picture. So okay, everybody, quick wave, a wave, and a congratulations from everybody, and we will look forward to seeing you here very soon.
Congratulations.
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 Congrats.
Congratulations.
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 Congrats.
Congratulations.
To hear your voice.
Congratulations.
Congratulations.
So with 158 congratulations, we'll say good night and sleep well and enjoy your week.
Thank you. Thank you for doing this.
Okay.
Okay. Bye.
Bye-bye.
Bye.